When a machine erupts with millions of volts, the air itself tears open. The resulting electrical arc burns brighter than the surface of the sun, pushing temperatures past 30,000 degrees Celsius and instantly vaporizing nearby metal. We are watching humanity recreate nature's most destructive force, inside a laboratory, entirely on command. And that presents a strange contradiction. Modern civilization relies on our ability to continually generate and manipulate the exact electrical forces that used to terrify us. For most of human history, a lightning bolt was a mystery of scale. Discharging hundreds of millions of volts in a fraction of a second, it was viewed as a divine weapon, a chaotic energy source far beyond human comprehension. Building a global power grid, building particle accelerators or semiconductor factories meant we had to overcome electricity itself. We had to cross the threshold from fearing the storm to engineering it. The initial breakthrough required a shift in perspective. Benjamin Franklin demonstrated that a lightning strike was governed by physical laws. It was simply electricity. By proving its electrical nature, a massive, unpredictable atmospheric event was reduced to a measurable, solvable engineering problem. But scaling up that physics was brutal. As early engineers pushed voltages higher using large rotating disks and static electricity machines, they hit immediate physical barriers. Insulation degraded quickly, and dangerous arcs would burst out of the equipment without warning. The underlying energy was no longer magic, but the mechanics of controlling it were barely understood. To use electricity, humanity had to learn how to cage it across escalating scales of power. By the 19th century, expanding cities and factories demanded enormous amounts of power. Yet engineers hit a wall. They couldn't efficiently move electricity over long distances. This diagram shows why. Whenever electrical current flows through a wire, some of that energy is lost as heat due to physical resistance. To reduce the heat loss across miles of wire, you have to lower the current. And mathematically, to keep the same power output while lowering current, you must increase the voltage. This relationship made extreme high voltage transmission an economic necessity. The transformer's invention allowed engineers to step up electricity to hundreds of thousands of volts, send it across continents, and then step it back down near the consumer. Managing those massive voltages required entirely new infrastructure. We built towering lattice steel structures, carefully expanding the clearance between cables to ensure the empty space around the conductors acted as a buffer. The shape of the modern electrical grid wasn't a design choice. It was a strict mathematical requirement dictated by the physics of resistance. Those tall towers rely on a specific physical property. Under normal conditions, the atmosphere behaves as a perfect insulator. It blocks electrical current from flowing between the massive lines and the ground. Here we see the physical threshold of dielectric breakdown. When the electric field grows intense enough, it violently accelerates neutral air molecules and strips electrons away. This ionization process forms a conductive plasma channel. At that threshold, the insulation disappears entirely. The surrounding atmosphere turns into a wire, and the system experiences a sudden, catastrophic discharge of lightning. Because high-pressure electricity is constantly searching for a path to escape, engineering a power grid meant learning to manipulate these invisible electric fields before they could tear the air apart. To predict these failures, engineers needed to observe them on demand. So they built dedicated high-voltage laboratories, massive spaces filled with towering capacitor banks and impulse generators. These facilities were designed to generate deliberate electrical chaos, routinely producing voltages measured in the millions to push industrial materials to their absolute breaking point. By striking scale models of city buildings, power transformers, and aircraft, technicians could isolate exactly where a design would fail under a real atmospheric strike. Every spark captured in these rooms yielded precise scientific data. Engineers used those artificial strikes to reinforce weak points, upgrade ceramic insulators, and redesign circuit breakers. Our modern infrastructure survives the violent forces of nature because we spent decades repeatedly striking it with our own manufactured lightning. The techniques developed to protect the power grid eventually allowed researchers to build complex scientific instruments. Inside particle accelerators like the Large Hadron Collider, immense electric fields are used to push particles to extraordinary energies, allowing physicists to dissect the structure of matter itself. On the opposite end of the spectrum, semiconductor fabrication facilities manage electric fields with extreme precision, directing currents across microscopic silicon structures measured in nanometers. Whether the electric field spans miles of underground tunnel or nanometers of silicon, the underlying physics of electrical control remains exactly the same. Now, engineers are applying these principles to fusion energy, attempting to stabilize the intense reactions found inside stars. Confining a volatile, superheated plasma inside a reactor requires highly precise electromagnetic fields built directly on a century of high-voltage engineering. To unlock an energy source capable of powering civilization long-term, we must maintain absolute control over these violent electrical forces. As we develop ultra-high-voltage transmission networks and scale up quantum technologies, the requirements for energy control will continue to climb. This leaves a lingering question. Can we scale our containment systems indefinitely, or are there strict physical limits to how much raw energy a human-made structure can hold? We never actually subdued the power of a lightning bolt. Its destructive capacity is exactly the same as it was thousands of years ago. We simply studied its behavior until we understood how it moved. By turning electricity into a measurable, predictable tool, human knowledge overcame human fear, and we learned to power the world.